All right, cool. So, yeah, hello everyone. It's yeah, I'll try and distribute these slides after today's lecture, and if not, you'll always have the recording. But yeah. So yeah, hello everyone. It's me again. I'm Rishav Kali's fourth year PhD student, and yeah, I'm excited to present to y'all LightningSim, which is
Breath.
one of the research projects I've been working on in the last couple of years. One of my biggest projects, actually. So I'm excited to show y'all what it's about. And we'll first, I'll just like go over like what it is and how it works, and then I'll do a demo at the end. And yeah, feel free to jump in with questions at any time, as usual. But yeah, so here's the outline for today. Gonna start with background on, obviously y'all know like what HLS is, but I'll talk about the different ways of simulating HLS designs and also a little bit of like how HLS works. And then I'll introduce the key idea behind LightningSim, and then I'll talk about how I actually implemented it in terms of architecture, show off some of the evaluations, and then go into some of the usage notes so that y'all can use it hopefully for your lab too. So yeah. So obviously I don't need to sell to you all the high-level synthesis concept. Of course, you know that it's easy to learn. It can be high productivity. You can get a lot done relative to how much you have to, how long it takes to write like Verilog or VHDL code. And it can be easier to debug because you can just debug your actual C or C++ code rather than having to debug the RTL design that you would have otherwise had to do if you're writing Verilog directly. But of course, you may not be certain about what the performance and correctness of this code that comes out the other side of this HLS synthesis process looks like. So, you know, you've written a full adder here, but how many cycles is that going to actually be? How many cycles is that actually going to take when the HLS tool implements it? And, you know, how do we actually test that it's correct? So there's three ways that you can basically get some sort of either simulation or information about the performance and correctness of your HLS design. The first, of course, is just C simulation, where you just compile the C code and make sure that it runs. And when it runs, if it gives you the correct result, then you have some confidence that your design is correct. And if it doesn't, you can go and debug that. But it only gives you a functionality check. It doesn't tell you anything about the performance of your design, right? Because, of course, the performance of your C code and the performance of the HLS output may not be directly correlated, right? You can have fast running C code that results in a really slow HLS design or vice versa. So you don't, just because with C simulation alone, there's really no way to tell how fast or slow your design is going to run. So that's where, after you run the HLS synthesis process, you can actually end up with an estimated circuit performance. You've seen that synthesis report that Vitis HLS gives you after you run synthesis. It will say, you know, that this function is estimated to take this many cycles. These functions are estimated to take this many cycles. But that is just an estimated performance. And of course, it doesn't give you any functionality check, really. It just tells you how many cycles it thinks your design is going to take. And finally, for the most accurate check of both performance and functionality, you can run C-RTL co-simulation, which essentially what this does is it takes the actual Verilog or VHDL output of the HLS synthesis process and runs it through a standard simulator. The one built into the Xilinx tools is called XSim, so it runs the XSim simulator on your Verilog or VHDL output and tells you the correctness and the performance of the design after you run that. So this performance is closer to cycle accurate because it's actually simulating every cycle of the Verilog code. So those are like the three ways that you usually, at least like during the HLS development process, you probably run C simulation a lot to check when you're developing your code, you're checking that it's correct. And then you might run HLS synthesis to check the the estimated performance of your design, make optimizations there, and then eventually you'll run CoSim to do a final, or not necessarily final, but a more thorough check. Tells you more about the performance and correctness of your design. So as I just mentioned, if you want to know if your design is correct, you can of course do C simulation, but note that since this is just running the C code, it's only telling you that essentially the input to your tool is correct, right? You're making sure that the algorithm that you've written is correct, but you can't really know for sure that the output of the HOS tool will correctly follow what you intended with that. So just because your input is correct doesn't necessarily mean that the HOS tool will do exactly the right thing, especially when you have certain pragmas in HOS can cause your design correctness to or your design to be incorrect if you use them incorrectly and things like that. So it's limited and it's not necessarily reliable. And meanwhile, of course, you can do CRTL co-simulation, which is much more accurate, but it can be much slower, as we'll talk about. And then for the performance of your HOS design, as I mentioned, the HOS synthesis report will give you rough estimates, but these estimates are from static analysis. So essentially, your the Vitis HOS tool is just looking at your HOS code and it's trying to see, okay, like, this loop looks like it's going to run this many times, or you've specified this loop will run this many times, and so it just multiplies how long that loop is going to take. So it's basically, it can only estimate based on what it can gather without running the design, right? It doesn't like run a test case and see how long that actually takes. It's just looking at the static analysis, just what you can infer from the code itself. And CRTL co-simulation is a much more accurate way to get your performance estimates because you can actually run a specific test case. You can actually see like how many times loops run and what's happening with like FIFO channels and other things within your design. So this can be much closer to cycle accurate. So when I was so this is sort of to motivate why I even started working on LightningSim in the first place. One of the first projects of my PhD career was a project called FlowGNN. And what this was I was writing in HOS an accelerator architecture for a suite of graph neural networks. So these are just pretty complex machine learning designs. And the goal, of course, was to be fast. So I had to optimize these heavily. I would be in this cycle where I would edit the code, test it out, run synthesis, see what the performance estimates look like, edit the code again, run synthesis, see the performance estimates, and then eventually sometimes those performance estimates, as I mentioned, aren't precise enough because they're just looking at what the code itself looks like. So I would need to run CoSim and get more accurate performance estimates. And of course, that can be pretty painful. So it turned out that especially towards the end, as my design got more and more complex, each synthesis run alone took almost 15 minutes. So I would edit like maybe one line of code, and then I have to wait 15 minutes to see what the performance estimates even look like. And then if I needed to actually get more accurate performance estimates because the synthesis report wasn't telling me the complete story, then of course I had to run CoSim, and each CoSim run for this took over an hour. So this was really frustrating to work on. So hopefully you can sort of get a sense of why what really motivated me to develop this tool. And this is jumping ahead a little bit, but LightningSim actually is able to reduce this a lot because it can actually do close to cycle accurate performance estimate even before synthesis is done. And we'll get into how that works, but essentially you can see here, LightningSim took about 2/3 of the way through synthesis, it was able to actually give me performance estimates that are close to cycle accurate. But anyway, going back to, of course, these three types of simulation, you can see that there seems to be this sort of trade-off between speed, of course, C simulation being the fastest, RTL co-simulation being the slowest, and accuracy, where C simulation, of course, is the least accurate, gives me the least information about the functionality and no information about performance, of course. And CoSim on the other end, which gives me cycle accurate performance estimates and gives me deep functionality verification on the final design. So the goal, though, was, or the idea was, could we have something that has the speed of C simulation combined with the accuracy of co-simulation? And that's what LightningSim is trying to be. And it's the key idea here is that it's not a trade-off, but actually has advantages of both sides. So if we compare C simulation and co-simulation, as we just mentioned, there's the speed trade-off, and C simulation, of course, doesn't have any cycle level estimates, and it only does a shallow functionality verification. But LightningSim sort of combines the best of both worlds between C and RTL co-simulation, C simulation and RTL co-simulation, where we can get speed that's almost as fast as C simulation, depending on the design. It can be, as you saw, it can complete faster than synthesis, and the actual speed of the simulation itself can be comparable to C simulation if you've already run synthesis. And of course, it gives you cycle accurate estimates of the performance of your design, just like RTL co-simulation does. And it does deeper functionality verification than C simulation alone. The specifics there are not super important, but basically it can test everything almost up to the point where you actually have to generate the RTL. It can test, it can make sure that the HLS tool is doing the right thing for a lot of the synthesis process. And then it also introduces a few new features that aren't available in any existing simulation tool, such as incremental stall analysis and estimating the fastest, or suggesting the depths of FIFO channels. And we'll talk about these later in the talk. But yeah, so the key insights here, you first we'll need to go over how HLS synthesis actually works under the hood. So as you've probably saw in the previous slides, there's actually 3 steps to this. The first is called front-end compilation. The next is scheduling and binding, and the last is RTL generation. So the first thing that the HLS tool does is is to do front-end compilation. And what this does is it generates what's called LLVM IR, or IR being intermediate representation. This is a lower level representation than C or C++. Things like if-then statements, loops, all those stuff get compiled down to branches, and you have a limited set of operations you can do, and there's exactly one operation per line. It looks a lot like assembly, but actually it's higher level than assembly, because you still have this code that's divided into functions. You still have data types on each variable, and you still have variables, and things aren't assigned to registers yet. So it's higher level than assembly. It's actually agnostic to this specific computer architecture that you're running on. So this is actually how C and C++ compilers like Clang normally work. So you give it your regular C++ input code as input. And the first thing it does is it generates this LLVM IR from it. But then after that, all behind the scenes, this is completely transparent to the user. It takes this LLVM IR and lowers it to this assembly where you actually end up with, of course, registers and stuff that actually runs directly on your hardware, on your x86 or ARM hardware. But the LLVM IR is this intermediate representation that sits in the middle. The point of it, the original reason why it's designed, is that it provides something that sits between all sorts of different input languages like C or C++ or even Rust, and those can all get translated to LLVM IR, and then the LLVM IR can be translated to x86 assembly or ARM assembly or any number of computer architectures that are supported by the LLVM project. For the purpose of HLS, though, we actually stop here because the LLVM IR is repurposed by Vitis HLS as the starting point for the hardware-specific stuff that we'll get into next. So we just do the front-end compilation. We don't actually, of course, get the assembly instructions. We just stop here. And then with the LLVM IR, the next thing we do is scheduling. So we look at each instruction in here, and we essentially generate a finite state machine from it, or the Vitis HLS tool will generate a finite state machine. And what this finite state machine does is decide when each operation in the LLVM IR is going to execute. So if you have 2 adds and they don't depend on each other, then Vitis will say, oh, I can put these in parallel. So let me schedule them into the same state of this finite state machine. And if I have a loop and the loop iterations are pipelined, then I can then it will schedule that accordingly, where you have different stages that the pipeline can be in, and it will add the state transitions between those and whatnot. So basically, this is just deciding. This is the first hardware specific step where we're deciding for each software instruction, when will this execute in hardware in a finite state machine. Of course, the finite state machine can have loops. It can have things that, like go back and repeat and whatnot. But that's basically this is actually this is what's shown in the schedule viewer in Vitis HLS. So like for the most part, it's sort of straight line forward. But if you have like a conditional or something, you might skip some of it. If you have a loop, you might go back to some of it. But essentially what it is a state machine. And the key insight here that really motivated me to develop LightningSim is that this is usually 1 clock cycle per state. So when you're looking at the schedule viewer, when you are developing an HLS design, a lot of the time what you'll notice is that you're looking at the schedule viewer and you're trying to see like how many cycles different like a loop might take. And that's just how many states are in the finite state machine that are shown in the schedule viewer. So if it shows like 0 through 6, that might mean that you have that loop takes 6 cycles, right? So usually it's 1 clock cycle per state. There are exceptions that I'll get to later, but basically the motivation was that if we know that this schedule viewer is almost equivalent to the number of clock cycles that it will actually take when we run this design on hardware, then can we use that to actually run a simulation, right? Like, do we even, we don't need to, at least for my purposes, I didn't need to know all the specific wires, all the specific, register values. I just need to know how long it will take. And for that, all I really need is the schedule, right? And then if that's the case, then this RTL, the Verilog VHDL output, doesn't even matter to us because we don't need to care about what the actual signals are. We don't need to care about any of that. We just need the finite state machine in order to do this simulation. So actually this RTL generation step, at least for the purposes of our simulation, is not even necessary. So that can actually save a lot of time. If we go back to that FlowGNN example that I mentioned earlier, I mentioned that it takes 15 minutes to do synthesis for that. Actually, the last 5 minutes of that are all just RTL generation. So if we don't need the RTL for simulation, then we can essentially get a simulation done in 10 minutes. And that's how I mentioned that LightningSim is able to finish faster than synthesis. This is why we don't have to care about the RTL generation step. All right. So any questions here before I move forward? Just so like key insights here. All right. Assuming there are no questions, I'll move on. So yeah. So now let me define a few terms that I use for LightningSim. So the first is stages. So as I mentioned, HLS generates a finite state machine for each function. And so I call those stages. And in particular, I call them static stages when we look at the schedule that we get in the schedule viewer in HLS, I call those static stages. Those are the scheduling results and only reflect the possibility of simultaneous or sequential executions of modules or operations. And what do I mean by that? Essentially, as I mentioned, if you have like 2 functions that can execute together, they'll be scheduled into the same stage. The loop body and the loop condition might be able to execute together. They'll be scheduled into the same stage. And then if I have a loop condition, then that might cause the loop body to execute again. So by possibility here, what I mean is that we have a loop iteration as like a possibility that might happen multiple times, or if we have a conditional, if we have like an if else, then both the if and the else will be scheduled into the static stages, but they'll be in different static stages so that we skip some of them if we do the if, we skip the other ones if we do the else. So essentially, it's the possibility of what might execute, not necessarily what will execute. On the other hand, I define this term of dynamic stages, and this is the actual executions under a given workload. So essentially, if for a particular test bench, I provide input data to the design, and because based on that input data, we have to run a loop maybe 4 times, right? Then what's going to happen is we're going to visit some of these states over and over. We're going to visit those loop states 4 times. So I will unroll essentially the static stages into what I call dynamic stages, where essentially if here states 2 and 3 are representing this loop, then we're going to have those same states 4 times for a loop that executes 4 times. So all I'm doing is I'm just taking the static schedule, and based on the actual execution, I'm just renumbering it based for each iteration for each actual state that is visited. Does that make sense so far? Because then next we have this is almost essentially this is almost the total number of clock cycles in a particular function, but then we have to deal with stalls. So the dynamic schedule exists per function, and when you have interactions between functions like function calls or reads and writes to FIFO channels or I/O with external memory, AXI I/O. I call these events. These are potential places that the schedule might stall because it has to wait for something else. So essentially, we might remain in this example here. We have 2 events, or actually, sorry, 4 events. The function A start, function B start, function A end, function B end, and they are all within this first stage, right? This first dynamic stage here. So depending on how long function A and function B actually take, we might actually have to stall and basically hold stage 1 for longer in order to wait for function A and function B to complete. So I basically insert these stall stages or stall cycles into the dynamic schedule in order to get our final number of cycles for this design. So essentially, in this example, cycles 1 through 4 are all what we saw as dynamic stage 1 here, and then the rest is as normal. We just take that many cycles. Does that make sense? Let me know if you have any questions. But yeah, that brings us to the key idea of LightningSim. So first, we obtain the static stages from HLS synthesis, the scheduling process. And then we figure out the dynamic stages based on a test bench execution trace. So we run a test bench, we trace what it does, and based on that, we sort of unroll that static schedule as we saw based on number of loop iterations, which conditions are visited, things like that. And then finally, we identify all the events, which are the potential stall points, and compute based on the entire simulation how many stall cycles we'll have in each function, and get the final cycle count for that. So that's the key idea. Now to talk about the way that we do this, the way that I actually implemented this, the architecture. I use a decoupled 2-stage simulation flow. So the first thing I do is I compile and run LLVM IR under a given test bench. And what that does is it produces a trace, as I mentioned, the trace indicating which loops ran, how many times each loop ran, things like that. And then I analyze that trace to calculate the design performance. So first, let's look at the first half of this architecture where I compile and run the LLVM IR under a test bench to collect a trace. So the goal here is, of course, we take the IR directly from that front-end compilation, as we showed from the HLS synthesis process earlier, and determine what instructions are executed under a given test bench. The problem here is that there's certain functions and certain parts of the code that won't compile because, again, remember that the HLS synthesis process normally stops at the IR, and then it just does its own thing with scheduling, binding, and RTL generation in order to generate the hardware code. It never actually needs to run the LLVM, right? But for our simulation, we're trying to run this so that we can collect a trace. So in order to do that, we need to fix certain parts of this LLVM IR that are not intended to run, right? So there are certain placeholder functions in the LLVM IR that's generated by Vitis HLS, and these placeholder functions, the code won't compile because they're just empty. They're just not defined, and so you'll get link errors at when you try to compile and link this. So the first thing we have to do is generate definitions for these functions on the fly. So what I've done in LightningSim, I have looked at a bunch of different HLS designs and the functions that are needed for them. So, for example, for FIFO reads and writes, the FIFO channel reads and writes, I've provided my own implementation for that, so that if the FIFO read write function is called, then it will call into my code and simulate a FIFO read or a FIFO write or whatever we need for the simulation to run correctly. So we fill in those functions. And then the second thing we need to do is actually log which instructions are executed. So if we just ran this as is, we wouldn't really know anything about like which loops were taken, right? Or which conditionals were used. So we need a way to trace that. So the obvious thing to do would be to, for every single instruction in this file, we would want to log, maybe like print something saying this instruction executed, and then this instruction executed, and then this instruction executed. But obviously, that's going to be a lot of log data. So instead, we're going to do the next best thing and look at basic blocks. So LLVM IR is organized into basic blocks. And what basic blocks are groups of instructions that always execute together. So they're instructions that have no branches in the middle of them. They might end with a branch, but within each basic block, execution goes line by line by line. There's no way to, if you wanted to jump out in the middle, that would generate a new basic block. So basic blocks, by definition, always execute together. So what we do is looking at these basic blocks. So in order to log which instructions are executed, we only need to log which basic blocks are executed, because we know that if a basic block executes, then all of the instructions inside of it are going to execute. So we just add these tracing calls, or essentially print statements to each basic block to let the system know that which instructions were executed, essentially. So now we know, like, if there's a conditional, then only the basic blocks for the if part or the else part will be executed, or will be logged, and not both of them. Or if we have a loop, then we'll have the same basic blocks logged over and over for that loop, as many times as that loop ran. And at this point, we are ready to compile and run this LLVM IR. And once we do, we get a flattened trace, basically just all the print statements that I added, of LLVM basic blocks. As I just mentioned, each basic block is logged once every time it's executed. And also, I log auxiliary information about the FIFO reads and writes, and external memory transactions, AXI transactions, because those will be needed to do an accurate simulation later. And then, using this flat, essentially text file, I look at the LLVM IR, and I map this into a hierarchy. So I say, okay, this basic block belongs to this function, and within that basic block, we have a call to a different function, and I just organize it into a hierarchy for parsing down the line, or analysis down the line. So that's the trace generation part. Any questions there so far? So there's a question that says, have there been times where the mimic LLVM functions are not accurate? So the implementation of them is usually pretty straightforward. Like I said, like, for example, a FIFO read, there's only really one thing that it can do. So usually the implementation itself is not is very straightforward. So it's not so it's usually always accurate. But later down the line, when I do the actual timing prediction for the trace for the stall analysis, sometimes that can be inaccurate, and I will actually get into that. Basically, when I do AXI transactions, external memory transactions, those can sometimes be a little bit off, but the actual functionality is usually easy to get right. Although there are cases where there have been cases where I haven't implemented certain functions. So I'll actually also briefly mention this at the end, but non-blocking calls. So where you try to read a FIFO and you either get a result of true if there is something in the FIFO and false if there's not, then those will actually those I haven't implemented at all. So actually that will just fail at compile time because it will just be like there's no definition for this function. But functionality is easy to get right. The cycle accuracy is trickier. Yeah. So yeah, that's as I'll talk about later. That is actually the reason that LightningSim is not 100% cycle accurate. But yeah. Any other questions so far? All right. If not, I will move on to the second half, which is trace analysis. So as we just discussed, we have this hierarchy of, or we have this trace for each function. We've parsed it into a hierarchy, so we know for each function exactly which instructions have executed. And now what we need to do is turn the static schedule for that function into a dynamic schedule based on what instructions were executed. So what I did in LightningSim is essentially I came up with a list of rules that model how the FSM executes in hardware, what the generated FSM does for a given set of instructions. So we have this trace of the basic blocks and we have the static schedule. And what I do is I essentially replicate the stages of the static schedule into a dynamic schedule based on this order of trace basic blocks here. So first we have like these two instructions execute. So I copy that over here. Then we have these two instructions execute next. So that gets copied over here. And then we have like this basic block. You'll see that there's some overlap with the previous one, with the previous static stage, which is why you can see in this diagram here, we have some overlap. But essentially these rules ensure that the FSM, or that my dynamic schedule matches how the FSM would have gone through the states in hardware based on what instructions were executed in software. So for a given input, we know which instructions execute in software, and based on these rules, we can figure out what that means for which states would have executed in hardware. So at this point, as I mentioned, we have our dynamic schedule of dynamic stages, and each of these is one clock cycle except for stalls, right? So the next thing we have to do is identify where events occur in the dynamic schedule, and events are just my name for points where stalls can happen. So as I mentioned, this includes function calls, this includes FIFO IO, and it includes external memory transactions. So I've highlighted those in purple here. So the next thing you have to do is figure out, do any of these stall, and if so, for how long? So that brings us to stall calculation, which is the next step. So the question to consider here when we're talking about stall calculation is when and why do events cause stalls? And the answer is that some events have to happen before others. So if we have a FIFO read in one function and a FIFO write in another function, the producer that's doing the write, that it has to reach that write before the consumer can read from it. If the consumer tries to read before the producer writes, then we're going to have to insert a stall into the consumer to ensure that the finite state machine doesn't proceed until the FIFO is ready to be read. So graphs are a natural way to encode these sort of happens before dependencies, where I would draw an edge from the I would make a node for the FIFO write and the FIFO read, and those nodes would be connected to everything else in the respective functions. But then I would draw an edge from the write to the read, and that essentially I can treat that as a constraint, saying that the write has to happen before the read. One problem, though, is that some of the dependencies are actually unknown during static analysis and must be captured on the fly. Static analysis here being just like at the point that we are at with where we have the dynamic schedules. One thing, like for example, dependencies based on the FIFO depth are actually unknown at this point. So one thing that we try to do within LightningSim is we'll talk about later, but if you change the FIFO depth, then we can do an incremental resimulation, but we can only do that if because essentially the start node and the end node of certain edges changes. So we can't just encode that into the graph as a fixed edge. We need to have some way to express that this dependency is unknown. So what we do actually is we just create a partial graph with the statically known dependencies, and we dynamically resolve the rest later. So here's an example of this graph construction. In this simulation, we have three modules. One is the top module, and then we have a producer module and a consumer module. And the producer is, of course, writing to a FIFO, and the consumer is reading from a FIFO. And what we do first is for each dynamic stage in each of these modules, we create a node, and then we have edges between these nodes to encode that stage 1 has to happen before stage 2, which has to happen before stage 3, which has to happen before stage 4, and so on. So the first the first event that we see is a function call event that at the top module, the consumer start event happens at stage 1. So what this means is that the consumer module, the first stage of the consumer module is not going to happen until the first stage of the top module happens. So we draw an edge according to that dependency there. Then we have this producer module. We have the producer start at stage 2. So of course, that just like before, that means that the first stage of the producer has to happen after the second stage of the top module. So we draw an edge from the second stage of the top to the first stage of the producer. Then we see that there's a function call event for the producer end at stage 4. So what that means is that the top module, when it gets to stage 4, if the producer is not done, it's going to wait until the producer completes. So what we do is we draw an edge from the end of the producer module, which here is stage 6, to the stage 4 of the top module. So if this would have otherwise reached stage 4 before the producer module is finished, now it would stall to wait for the producer module to finish. So we've encoded this dependency here. And similarly for stage 5, we have the consumer end. So we draw something from the end of consumer to stage 5 of the top module. Now we get to the FIFO events. So the first thing we see is that the producer does a write stage 1 to a particular FIFO, and that FIFO is then read at stage 3 by the consumer. Well, then of course that means that stage 3 of the consumer can't proceed until that write has happened. So we add an edge from the write to the read within this graph to encode this dependency. Similarly, we see that the producer is writing at stage 3 and the consumer is reading at stage 4. So we draw an edge from producer 3 to consumer 4. Then we have a write at producer 4 going to read at consumer 5. And then we have a write at producer 6 going to read at consumer 6. So we've drawn all these edges so that if for whatever reason the consumer module would have reached one of these stages before the producer, then it will stall to wait for the producer. So at this point, we've captured these read after write dependencies, right? Because of course, we can't read an empty FIFO. We have to wait for that write to happen before the FIFO read can proceed. But what about write after read dependencies? These are, if the FIFO is full, then the write will have to wait, right? If we have 30 elements in our FIFO and we have done less than 30 read, and we haven't read anything from it yet, then we're going to have to wait until at least one of those reads happens in order for the write to proceed. Otherwise, the write will stall until the FIFO is no longer full. But of course, this depends on the FIFO size, which is not known yet. So essentially, you can imagine that, like for example, this second read of the producer, if the FIFO size is only 1, then it's going to have to wait until the first element is read from the FIFO. But if the FIFO size is more than 1, then this can proceed immediately without having to wait. So the edge from this, the write after read dependency for this node is actually not known yet until we know the FIFO size. So our solution is to create floating edges, which are just edges that point to a node, but don't have the starting point at this time. We encode some metadata so that we can resolve the starting point later, but for now, it's sort of just floating in midair. So as I mentioned, if the FIFO depth is 1, the first write never has to wait, so the floating edge is ignored. The second write has to wait for the first read, which is at stage 3 of the consumer. The third write has to wait for the second read at stage 4, and the fourth write has to wait for the third read at stage 5. If at any point it didn't wait for those, then the FIFO would be full at that point, so that's why we have to wait. But if the FIFO depth is 3, then that automatically means that the first 3 writes never have to wait, right? Because regardless of how many reads have happened by the time we get to, say, this node, there's still going to be space for at least one more. But after the first 3 writes, the fourth write now has to wait for at least one element to be read, right? So we can draw an edge from the first read to the fourth write, or at least we resolve the edge. So notice that this is the compiled graph, and then this is the runtime view of that graph. So I'm not actually changing the graph at all. I'm just changing how I look at the graph when I encounter one of these floating edges. In general, the formula is just that the nth write has to wait for the n minus depth read. So at this point, we can now traverse the graph. And so calculating the final cycle count of our design just amounts to calculating the longest path through this graph. And so this is really good for design space exploration when you have FIFO channels in your design and you don't know what depth to make them. You can compile this graph once from a single simulation, and then you just change the depths over and over, and all you have to do is just traverse this graph. And the graph just sits in memory, read-only. You can just traverse it over and over very quickly in milliseconds and get simulation results super fast. So this is especially good on multi-core systems because, as I mentioned, the graph traversal doesn't actually need to change anything about the graph. It just changes how it traverses it. It just changes where those floating edges resolve to at runtime without actually having to write back to memory. So the simulation graph can be in shared memory, and then you can have a bunch of cores, all with their own FIFO depth configurations, all doing their own graph traversal, and you can do this very fast. And basically do this design space exploration in parallel on multi-core systems. You can contrast this with closed simulation, where if you change the FIFO depth, it has to rerun the entire simulation because it doesn't have a way of encoding these dependencies in this flexible way. I'll go through evaluations pretty quickly, but we evaluated LightningSim on 33 benchmarks. 23 of them are just sample designs from the Vitis HOS sample repositories. 5 of them are actually sort of real-life algorithm implementations from this book, Parallel Programming for FPGAs, which you've probably seen in this class, maybe. And then 5 of them are the FlowGNN graph neural network accelerators that I was talking about. Each of them is over 1,500 lines of code. And as I mentioned, is there a question? Okay. If there, feel free to interrupt if there are any questions I need to know. But yeah, so right, we also tested on 5 graph neural network accelerators from FlowGNN, which, as I mentioned, takes like 15 minutes to synthesize, can take an hour to co-sim, so it's pretty long. We used 2021.1 as our baseline and evaluated the accuracy and performance. What we found is that it's 99.9% cycle accurate to co-simulation. It's 100% accurate for 26 out of the 33 cases we tested. Of the remaining 7 cases, there's 2 sample designs that are 1 cycle off, and the other 5 cases are within 0.2% error. And so this is actually going back to a question that was asked earlier. The reason that LightningSim is not 100% cycle accurate, the way that I model the timing of the external memory transactions is not perfect. So I I tried to look at the Verilog that's generated to try and come up with a model that's as accurate as possible, but it's quite complex. And since I'm not actually simulating any RTL, it is just a model. It's just what I've implemented. So that's why it's not 100% cycle accurate. But in theory, it should be 100% cycle accurate if we had a perfect XC model. But the speed up results are pretty significant. So we have speedups ranging from 5.5 times to 146 times over CoSim, and actually larger designs achieve the greatest speedups. So as I mentioned, one of the FlowGNN designs, the co-simulation took an hour 10 minutes, and LightningSim on the same design takes 29 seconds. So I'm pretty happy with that. And then, as I mentioned, we also have the feature of doing incremental resimulation, where you can change the FIFO depths and just resimulate with different FIFO depths, and that's under 20 milliseconds for all the benchmark designs. And so we're hoping that this is helpful for evaluating deadlocks and stalls for data flow designs really quickly. And I see there's a comment in the chat that Lab 2, it brought the simulation from 4 hours to 30 minutes. So I'm glad it works. So yeah, so LightningSim is available on GitHub. You've probably already seen this at this point, but it has I've packaged it using Conda. So in theory, you can just run this one command in order to install LightningSim. I also did make some updates, by the way, if you were testing earlier this week and you were getting like linking test bench errors and things like that, especially for newer versions. The newest versions of LightningSim, I released one this late last night. Should fix that, hopefully. No guarantees, but I've been trying my best. At least for 2020, at least if you use 2021.1, it should definitely work. But other versions I can't guarantee. But yeah, and then there's a tutorial available. Maybe we can, I might go over a few of the examples here. But like this, we actually presented this at a conference in May, I believe, of last year. And so this is like just some hands-on examples. I'll do a couple examples real quick at the end. But first, I do want to mention a few usage notes. So oh, I see a question. Is it possible to install on the server? So yes, it is. And that's what I'm actually about to mention here. So first thing is if you're on one of the Georgia Tech ECE servers, you should have, I think you have to use Bash. So the provided Bash profile, this is one of the startup scripts that launches when you SSH in. It will launch the C shell automatically, CSH automatically, but that is not, as far as I can tell, it's not fully compatible with Conda. Conda is not able to set the environment variables for the compiler and stuff correctly when you use C shell. So it may like seem like it installs correctly, but then when you actually do like linking, when you actually run LightningSim, you might end up with a linking test bench error because it doesn't use the correct compiler. So so C shell doesn't seem to work. The easiest way to use Bash instead, well, you can just type Bash in the terminal and it will, of course, run Bash, and then you can do all your work there. Or if you just want to use Bash all the time, which is what I do, I don't like C shell, you can rename the Bash profile file to something else. Oops, sorry, I didn't mean to do that. But yeah, so the Bash profile, you can just rename it to say bashprofile.old or something like that. And then the next time you SSH in, it will drop you directly into Bash. So that's what I do. The other thing is that Conda is actually already pre-installed. You can install it yourself without needing root permissions or anything, but ECE does maintain their own Conda installation. And so you can add this line to your my-bash-rc. No, by the way, I should mention my-bash-rc, if you haven't used the ECE servers too much before, bash-rc on its own is the startup script that is launched every time you launch Bash, but that is managed by the ECE department by default. And so they provide another script, or they check if there's another script called my-bash-rc. If my-bash-rc exists, then it will execute that as well, in addition to the stuff that they set up. So you want to add this line to your my bash RC, and this will enable you to use conda within bash. You may have to restart your shell after doing so, but you should be able to use conda there. And then another thing I should mention for LightningSim, the I have oh, this is another thing I updated recently. It now defaults to command line mode because I wasn't sure if y'all would have trouble running the web server GUI. So you can still use the GUI if you do -- GUI. But if you want to use the command line mode, which is now the default, I would highly recommend that you output all the write all the output to a file using this syntax. Just use the right angle bracket and then the file name you want to write to, because it does log each invocation of like the exp helper function individually. I don't have a way of filtering that built into LightningSim right now, but if you just log it to a file, you can just like grep for the file, grep for the lines you want, or or I guess exclude the lines that you don't want after the fact. And also you won't spam your terminal. So you won't end up with a bunch of output just like unreadable. So yeah, definitely if you run this on the server, I would definitely recommend this, especially with the latest version if you're not using the GUI. Another thing, so if you want to run a long job, some of you might already be familiar with tmux, or there's other similar programs like Screen, but I use tmux. So tmux will essentially, it stands for terminal multiplexer, and what it does is it lets you basically start a shell and then detach from that and let that run in the background, and then you can disconnect your SSH, you can shut down your computer, do whatever you want, and then later you can, when you start up your computer again, you SSH back in, you can reattach to that existing shell like nothing happened. So you can detach and reattach, and if your SSH connection gets disconnected, there's no problem. You can just reattach as usual. So it's really handy when you're running things that are that take a while. You can avoid any issues with, if your SSH session disconnects and whatnot. These are just the basics for like how to use tmux. If you just run the command on its own, it will start a shell session. And then within tmux, you can all commands that actually go to tmux itself start with control B. So control B D is the main one that I know, which is detach a session. So you can start a shell, you can start LightningSim, and then you can do control B D, and then it will say detached from whatever shell session. And then later you can do tmux attach, and then it will pop that session back up again. So very useful, just in general, not just for like LightningSim or anything, just like when you're using the Linux terminal. And then finally, I should mention that I did mention, I only tested this on 2021.1, and I'm aware that some of you are trying to try it with 2024, which is great. Please let me know how it goes, because I actually don't know if the accuracy it will be up to par. Mainly because, as I mentioned, the AXI interface model is based on what I saw in the Verilog output for 2021.1, and I think they might have changed that. I'm not 100% sure, but I think they changed it. So if the results are wildly off, that may be the reason. Do let me know. Feel free to post on Piazza, actually. I would be curious to know. Bonus points if it is off and you want to take the arduous task of trying to make a pull request to fix it. But it's probably a pretty big undertaking, so I would not suggest doing that unless you want to maybe like do that as like a separate project outside of the class. But, feel free to reach out to me if you're interested in contributing. I'm happy to take on some new help. So yeah, that's it in terms of the presentation. But yeah, so I think we should have like 20 more minutes. So I'm just going to briefly go over like installation and usage like in a terminal, and just do a quick example. I'm not going to do the lab 2 example because that does take a while to run, but I will at least do some of the examples from the tutorial, which again, the tutorial link is here. lightningsim-doc.rtfd.io. And then I think you can actually, you don't have to put all of that part, but that just takes you directly to the tutorial if you don't, if you do. So, right. That's also available. I think if you go to the Shark Lab website and then under open source, and then click on this documentation link here, it takes you to the same place. So yeah, so I'll just go ahead and do maybe the first couple of examples, or maybe actually I'll do the second example. The first one is sort of showing if you were using the GUI for LightningSim and the GUI for Vitis HLS side by side. In it shows like how you might use it in a development workflow. But I'm just going to go ahead and go straight to the second one, which is just a more realistic example, I guess. Yeah, it's a fast Fourier transform kernel that I got from the Parallel Programming for FPGAs book. So I've already actually cloned the this repository to doc. Right. Examples, example 2. And you can, if you go to this set up a local environment thing, it will tell you where to clone it from as well. It's just the, this link here, download the examples. You can try this out on your own time as well. But for now, I've already cloned it. I haven't actually installed LightningSim yet, so let me go ahead and do that. The conda command to install LightningSim, or first let me go ahead and set up conda because I haven't done that, and you can tell I haven't done that. Oh, also I'm using Z shell, but the instructions should be the same for bash. So, or actually I'll go ahead and use bash just to make things consistent. Okay, so right, so I still don't have conda. So let me go ahead and set that up. So the easiest way to do it, or you can, if you don't want to have to execute a command every time, what you want to do is you want to go into your my bash RC, and yeah, I'll just do it here. I already have a bunch of stuff in this, but yeah, the command that you want, I have this in the PowerPoint as well. You just do eval and then quotes, and then this is a shell substitution, so just opt conda bin conda, and then shell.bash. And I'll post either these slides or a Piazza post with this command as well, so that you'll have it for reference. And then either you can restart your shell now, or you can just run that. You can just source the my bash RC command again, or my bash RC file again. Dot being a synonym for source here, so either way works, either dot or source. But now I should actually be able to run conda, as you can see. And I'm going to go ahead and create a conda environment with LightningSim in it. So the as I mentioned, this is both on the GitHub here, and it's also in the tutorial docs here. So I'll just go ahead and use the GitHub command. And make sure to replace this env name with whatever environment name you want to use. So I'm going to call this EC893. And just wait a minute for it to install. And hopefully it doesn't take too long. Conda can be kind of slow sometimes. You can also try Micro Mamba, which is faster, but you do have to install that yourself if you do that. Mamba is just a faster version of Conda, sort of a drop-in replacement, but we already have Conda, so you can just use that. And we just wait. Didn't take as long when I was testing it earlier. Okay, there we go. So yeah, to activate this environment, we can use this command. If you've never used conda before, this is just basically loading in the the path and shell environment that we need so that we can now run LightningSim. So you can see actually now it is in, I can actually like run LightningSim commands. So now I am going to go ahead and go to that example directory. Let me see if there's anything else I wanted to. Yeah, no. Okay, so if I go in, I'm already in example 2. I need to pass the path to the solution. Notice it wants the solution directory, not the project directory. So usually that will be something ending in solution 1. So if I'm in this directory, obviously it's just solution 1. If I'm in the previous directory, it is going to be something like, example 2, solution 1. But yeah, whatever the solution directory is. So I'm just going to run this. Oh, my bad. I didn't actually, I don't have the Vitis tools sourced either. So this is, obviously the Xilinx tools are available on the server. So you do have to, but you do have to specifically source them. So you can do source tools, software, Xilinx, Vitis, either Vitis or Vitis HOS. They both will work. They both load the same tools actually. So I'll just do Vitis and then latest, or I'll just do 21.1 because I know that works. Or actually, oh my bad, Vitis HOS 2021.1. Yeah, okay. Yeah, the 2021.1 directory only exists in Vitis HOS, but you can also use latest, as I mentioned. I'm not sure if it will be as accurate. And then settings 64.sh. And then, oh yeah, this is a harmless warning for 2021.1. But if you do one of the other versions, you won't get this warning. But I'm just going to use 2021.1. So now I should actually have Vitis HOS on my path. Yep. And now I should be able to run LightningSim. So what was it? Yeah. And as I mentioned, it defaults to CLI mode now. You can pass -- GUI if you want the GUI. And hopefully this works. Usually it doesn't take this long on analyzing project. I'm not sure if I... Oh, I guess I didn't... Oh, maybe I didn't... No, I thought I... Sorry, guys. I do not know what happened to my examples, but I'm not going to bore you with running that from scratch. So let me just do an existing project on my other server. If it actually loads. Do I have something else? Sure. Oh, lab 1. Okay, that's a good idea. Yeah, I'll go ahead and clone lab 1 and synthesize that. Thank you for the suggestion. Sure. JC. Oh, already. I'll do the COSIM later. Just gonna do synthesis for now. Let me go ahead and run synthesis real quick. Also, of course, feel free to jump in with questions at any time. Now would be a great time for while we're just waiting for this to run. You can also see the 3 steps that I was talking about. Of course, the first one, front end compilation, it calls that architecture synthesis, but it's all the optimizations that happen above this line are the front end compilation. And then we have scheduling and binding, which it shows as implementing module. And then we have generating RTL. So that's where, so you can actually see that happen. But yeah, so now hopefully I can just do project 1, solution. Sweet, okay. Yeah, I should probably document this better, but if it gets stuck at analyzing project, 90% of the time it's because the project doesn't exist. So it's not synthesized or something. But yeah, you can see here it printed the the cycle counts for the top module and the one below it. So it says that this one takes 123 cycles, and this ran the pipeline in it ran from cycle 9 to cycle 115. And then you can also get that information from the GUI. Let me see if I can pull. Let's try. Let's try this. GUI is meant to be used in theory as like an interactive, like alongside your development. That's why by the default behavior is to wait for each synthesis run. Uh, oh yeah, and you can see the output here. I guess I don't show that in the CLI, but and then finally we have this is the same information that was in the yeah. Oh, the FIFO tab. So this design doesn't have any, but actually let me see if I can show you the FlowGNN one, because that one you can actually, yeah, this shouldn't take too long because I think I already have it. So like 9. Yeah. Okay, so this is one of my FlowGNN designs, as I mentioned. I didn't install the new one. Give me one sec. Or actually, did I? I might have installed it under the name demo. Maybe I didn't. Oh well. Yeah. So the FIFO tab is specifically for adjusting the FIFO depths. So that's what I was mentioning with the incremental resimulation. You can just run LightningSim once, and it will store the graph, and you can manipulate the depths from the FIFO tab. So that's what. Hopefully, if this install doesn't take too long, I'll be able to actually show you that. Perfect. Okay. And let me go ahead and source the 2021 version. And then not this Lightning project solution line. Oh, GUI version. Forgot. There's a flag you can pass, by the way, on the command line for you can if you're using GUI mode, you can also pass skip wait for synthesis. I've considered making that the default, but I'm not sure how people use the GUI, to be honest, or if anyone uses the GUI. Okay, great. So does LightningSim support some sort of schedule view like CoSim does? Eventually, hopefully. I was actually thinking I am gonna try and make this dump a VCD file to do that sort of schedule view, but right now the best we have is the CLI output. If somebody would like to do that, it actually wouldn't be that difficult of a thing to do. We just need to because all the data is there. You literally just need to dump it in a format that we can visualize as a schedule view. But yeah, right now the answer is no, unfortunately. But it's not. It's basically just engineering work. It's not like a very hard problem to solve. So hopefully, eventually, I just for the papers and whatnot, this is this is fine. But yeah. Okay, yeah, so this is how long it takes to execute this is the number of clock cycles for the GIN graph neural network. And you can see that it actually uses some FIFOs. So these default numbers come from whatever you specified in your design. Yes, the latencies is just cycles without period. The period, you can always just multiply it by the period in your synthesis report, but that might not be accurate. In theory, you would want to multiply it by the like post implementation number for period. So but yeah, no, this is just number of cycles. But yeah, so for the FIFO depths, yeah, so this right now is just whatever I have specified in my design, but you can like reduce this to whatever number you like and see if these latencies change at all. In this case, they don't. This design is not very sensitive to the FIFO depth, except that if you make it too small, then it will deadlock. So this is a very fast way to test that. But yeah, I think it actually is sort of sensitive to MP-in, but I'm not sure. But yeah, this I think I do have an example in here where of a design that has more sensitivity to the FIFO depth. It might be this one. No, not this one. But is it even possible to calculate the period without synthesis? It's possible to estimate it from HLS, which is what the HLS tool does, of course, but no, without or I don't know if you're referring to synthesis as in the HLS synthesis or synthesis as in Vivado synthesis, but the of course HLS synthesis is required to at least have an estimate of the period, and then Vivado synthesis and implementation will give you a more accurate will tell you the actual period post implementation, which yeah. So LightningSim, by the way, does rely on HLS synthesis, of course. You still have to have the schedule, but it doesn't need anything in terms of the period or whatnot. Like it doesn't look at that. In theory, I suppose I could like also implement something that just multiplies this by the period that you get in the report, but I have not done that yet. It's but it wouldn't be too difficult to do. But also, I don't know how useful that would be because again, that period is just an estimate. It's not very good. But yeah. But yeah, so that's the GUI. There's also a Python API, and if you're curious about that, you can run this last example here. And I'll show you the Jupyter notebook just to give you a taste of that. But example 5, here it is. Yeah, so you can run the everything that happens both in the GUI and the command line. You can do that here, and you can also do design space exploration for the FIFO depths here. You can do like get FIFO design space and then run this DSE command or DSE method, and it'll tell you the different design points. So yeah, and I think that's about everything I wanted to go over. And we're about at the end of class anyway, so if anyone has questions, feel free to ask now. Oh, a bit off topic, but how do you have your terminal give autocomplete suggestions? So I have this set up with this is the Z shell. So the Z shell on its own, I think it actually might be installed on some of the servers, although it's a little bit of an old version, I think. So, okay, I should start with this. So my bash profile, I have export shell equals Z shell. I have it installed. I compiled and installed it myself, and then I just execute that. And then I also, on top of that, I have the Oh My Zish plugin. And so you can just do this install command, and it comes with a bunch of themes and plugins. And one of the plugins is called I think it's literally just called like something autocomplete. I don't remember. Let me check. Zish auto suggestions. So this is very handy. I am very picky about my terminal, so I like to try and make it as efficient as possible. Also, even if you don't use this, you can at least use Control R, which works in Bash as well, where here, actually, I'll just give an example. Oh, I have this set up with Fuzzy Finder, but even without Fuzzy Finder, you can do Control R, and then you can start typing a command that you've typed previously, and it will find that command. And you can keep doing, like, so if I do ls, Okay, this is not a great example, but yeah, Control R is the easy way to get that without messing with your shell too much. But yeah, anything else? All right. If not, I think that's all for today's class. So thank you all for joining. I will be on I'll be looking at Piazza every so often if y'all have any questions for me, or feel free to email me directly if you'd like. But yeah, thanks again, everyone. Have a great rest of your day.